chance or probability is not about luck. It's a useful tool that can be used to work out important things like the probability of contracting a disease or the chances of having either a boy or girl. Hi.
Hi.
Is this your son or daughter?
Daughter, this is Alexandra.
Alexandra, hi. And when you had Alexandra, did you have any sort of preconceptions, pardon the pun, as to whether you're going to get a boy or a girl?
I think there was a slight preference for a girl in terms of what we wanted, but we had no idea what it was going to turn out to be.
Do you know that the chances of having boys and girls, well, do you think they're 50-50?
Yep.
You sure about that?
Yes, I am.
And you've proved it? You've had one boy and one girl?
It. Yeah.
I don't know. I think it's 50-50.
If you had done your arithmetics, you would have found out that 51% of all children born are in fact boys.
51%? Is that right?
Some families have more boys, some families have more girls, but still most people think that your chances of having boys and girls is about 50-50. Not true. If you take a spread of population in Australia over the past 5 years, you'll find that boys are actually a little bit more common. Jen, what's the gender breakdown of the kids in the group here?
The breakdown would be the babies would be predominantly girls, the toddlers would be mainly boys, and the 3-year-olds would be predominantly girls.
The statistical way of thinking shows us that a small number of observations may be random, like with the children in this centre. But if we increase the number of observations, we find a surprising pattern. On average, out of 100 babies born, 51 will be boys. So that's inductive thinking. Now, while we can't prove that deductively, we can use deductive arguments to calculate the chances of various outcomes or probabilities. For example, Oliver, what are the chances of having equal numbers of boys and girls in your family?
Like, if you have 18 girls, you had to have 18 mums.
Yeah.
And if you have 19 boys, you had to have 19 dads.
Excellent example of deductive thinking. Thank you, Oliver. If the probability of a boy is P equals 0.51, then the probability of a girl is Q equals 0.49. To find the probability of any particular composition of a family of n children, we use the binomial expansion of P plus Q to the power of n that we developed earlier. For a family of 5 children, the expansion is... So how do we work out the chances of getting 2 boys and 3 girls? Since the probability of a boy is P, we will need 2 powers of P for 2 boys, and also 3 powers of Q for the 3 girls. So the probability of getting 2 boys and 3 girls is given by 10P squared Q cubed. The value of this term is 0.306. So we have just less than 1 in 3 chance of getting 2 boys and 3 girls in a family of 5. Inductive thinking shows us the pattern, that more boys are born than girls. Deductive thinking lets us calculate the chances. Like mathematics, statistical thinking uses inductive and deductive methods, or patterns and proofs. The method of finite differences is used in finding the formula to a function. Perhaps the best way of illustrating this is with a circular object, like this pizza. If we make a number of straight cuts through the pizza, what's the maximum number of pieces of pizza we get from a certain number of cuts? No cuts gives...
1 piece.
1 cut gives...
2 pieces.
2 cuts give...
4 pieces.
3 cuts give...
8 pieces.
Wrong! 3 cuts give 7 pieces. Let's see how. Inductive thinking in this case has produced an incorrect result. We thought we saw a pattern, but it was wrong. This can happen at any time with inductive thinking, so we need to use deductive thinking to support it. We look for patterns, but we check we've found the right ones by using proofs. To use deductive thinking, we'll use a technique called the method of finite differences. Let's use n for the number of cuts and p of n for the number of pieces when there are n cuts. This is called function notation, and we say that P is a function of n. That is, P depends on n. We write P of 2 equals 4 to show the number of pieces is 4 when the number of cuts is 2. Applying the method of finite differences, we place n, the number of cuts, in the first row, and P of n, the number of pieces, in the second row. Then we take the differences of these P of n values, that is, the difference between 1 and 2, which is 1, between 2 and 4, which is 2, between 4 and 7, which is 3. Now we look at the row of differences and take the differences again, and we get 1 and 1. Deductive methods tell us that this process always ends up with a row of values all equal, as long as the original function is made up of positive powers of n. Now that we have a constant row, we can extend it as far as we want, and then work back up the table using addition instead of subtraction to find P of n for larger values of n, or more cuts in the pizza. Since P of 5 is 16, 5 cuts in the pizza can give us 16 pieces. This example shows us that we can't rely on inductive thinking alone. We have to back it up with deductive techniques or proofs.